happens to the atoms and molecules?
Oh, and now there's no sound. That's exciting. Why is there no sound? Exciting.
I want to talk about two things.
What happens when stuff dissolves? I mean, like, what happens to the atoms and molecules that make it up? I want to talk about two things here that you dissolve all the time: salt and sugar. These two things look very similar. They're both like what kind of white powders made up of little grains, and you can pour both of them into water and stir around. And you see the grains get smaller and smaller, and maybe break apart, until eventually they've totally disappeared. They've completely dissolved in the water. That's what you see with the naked eye. But if you had atomic vision, and you can see the atoms that make up salt and sugar, what would it look like as these grains broke apart and became invisible? That's what we're going to talk about here. So it actually depends whether something is an ionic or a covalent compound. It depends on what it would look like when it dissolves.
And what we've been looking at so far is what happens when ionic compounds dissolve. So this one should look familiar, okay?
So over here we have salt, and this is an ionic compound. This is what a grain of salt would look like, and it's made of sodium ions, Na+, which are metals, and Cl, chloride ions, these blue things here, which are nonmetals. So salt is an ionic compound made of metals and nonmetals. Sugar, on the other hand, is a covalent compound because it's made of nonmetals: carbon, oxygen, and hydrogen. And these nonmetal atoms are connected together into a molecule. So a grain of sugar would look like this. It would be a bunch of these sugar molecules all kind of lumped together. Notice that a grain of sugar is a lot more messy. It's not nearly as well organized as an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision, we're going to see that the atoms that make up this salt are going to come apart from each other. They're going to break apart, and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay? Now let's take...
So did that look familiar? Yes. Okay, good.
Take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms. So, to answer the question, what does it look like when something dissolves in water? The short answer is, it actually really depends whether you're talking about an ionic compound or a covalent compound. If it's an ionic compound, it's going to break apart into all of the individual atoms. But if it's a covalent compound, the clump of the molecules will break apart into individual molecules once it dissolves, but the molecules themselves will not break apart into atoms. They will stay as molecules dissolved in the water.
Okay. We're going to take a moment away from that and go here and just make sure we got everything that needs to go in here. So what went in that ionic box? I'll be honest, I don't remember. Metal plus non-metal? And what went in the covalent box? All nonmetals. Okay, and we have the lovely little pictures showing what happens. So if you remember originally, and I'm going to simplify my sugar molecule, okay? This whole thing here, I'm going to simplify by drawing just a little, black shape. We okay with that? That's a sugar molecule? When it started out, there were sugar molecules next to other sugar molecules, yes? What kind of thing is sticking the sugar molecule to another sugar molecule? IMFs. And remind me, are IMFs strong or are they weak? They are weak. What is it within the molecule that's sticking the atoms together? What are all these little things within the atom, or sorry, within the molecule, sticking all the atoms to one another? Those are covalent bonds. Are those strong or are they weak? Those are strong. So it is the weak intermolecular forces that break between the sugar molecules, and the strong covalent bonds stay intact. Okie dokie. And just a couple of vocab words here. Dissociation. If you associate with something, if you associate with another person, that means you come together and you meet, right? So if you dissociate, what does dissociation mean? You split apart, yes? Dissociate means to split apart. So ionic compounds dissociate in solution. If you started with calcium chloride that's all stuck together, when it dissolves in water, you end up with the positive ions floating around separately from the negative ions. And it is that separation that is the process of dissociation. Now the formula for sucrose, which is table sugar, is C12H22O11. Okay, so that's what you have in your kitchen is table sugar. And that is a covalent compound. What do you notice about its formula when it dissolves in water? What's the difference? Just the state, right? In the solid, you have all of those C12H22O11s, and they're stuck to one another. When you dissolve it in water, you still have C12H22O11, but each one is floating somewhere different in the water. So instead of saying they don't dissociate, the atoms don't dissociate, we say they disperse, okay? What happens when the bell rings at the school? The students disperse, yes? They just leave and wander out, okay? And that's essentially what's happening with the sugar molecules. All the sugar molecules are like all the students in the building, and when the bell rings, you all go your separate ways. You don't split into like arms and legs and torsos and things like that. That would be dissociation. And it's a good thing that you don't dissociate at the end of the day, because that would be rather awkward. Your parents might have some questions for the school, okay? So dispersion versus dissociation. Would we like to watch the other Tyler video today? Yes? Okay. Here we go. This one is, in fact, probably in the queue. Oh, there it is. Yay.
In this video, we're going to talk about how things dissolve in water to make aqueous solutions.
We're going to look at an atomic view of how water molecules dissolve solute particles, which is a process known as solvation. And we'll see that solvation occurs differently for covalent and ionic solutes. Let's start by making an aqueous solution, one that you probably made yourself many times. We'll dissolve a sugar cube in water. So here, sugar is a solute, and the water is a solvent.
So we will pause so you can fill that in. We have sugar is the solute and water is the solvent. Excellent. And I'm not quite sure what goes in that other box by water, but maybe we'll find out in a moment. Water. Water. I don't know.
We're making an aqueous solution of sugar. Now,
if you've ever dissolved a sugar cube in water, you know it takes some time to dissolve. It's not instantaneous. Let's take a closer look at what's happening during this dissolving process. Here's our sugar cube. And let's imagine we could zoom into it many times and see the atoms and molecules. We'd see that the sugar cube is made of trillions and trillions of molecules that look like this.
And if you were to count up, can I zoom in on this? No, I can't. Nope. Oh, and now I've distracted. Okay. We can't see it really up close, but if you are actually to count up all the little carbons in here, C, 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 you would find that there are 12 of them. And if you counted up all the hydrogens in there, you'd find there are 22 of them. And then O's, you would find there are 11, okay? So that's what the actual structure kind of looks like. And all of the atoms are what type of element? Nonmetals. So they are all nonmetals. Sugar is covalent.
Into it many times and see the atoms and molecules. We'd see that the sugar cube is made of trillions and trillions of molecules that look like this.
Table sugar is actually a compound called sucrose. Here's its chemical formula. And it's made of carbon, hydrogen, and oxygen atoms. Because these elements are all nonmetals, no sugar is covalent. Its atoms are connected by covalent bonds made by sharing electrons. And there are different ways that we could show the molecules. So here, we're representing the sugar molecules with a 2D Lewis structure.
We are going to learn how to draw Lewis structures this year, but not for anything nearly as complicated as sucrose. Okay, we will do very simple Lewis structures.
Shows the covalent bonds. If you made this into a ball and stick model, it would look like this. But a more accurate depiction of sugar is actually closer to this. We call it the 3D model,
which is also known as the space filling model. Yes, so we have the Lewis structure, we have the ball and stick in the 3D. Yes, yeah.
It's a bit blobby and kind of hard to see all the atoms. But we're going to use this model for now because it will better illustrate what we're talking about here, which is how molecules interact. Now, let's look at water, which is our solvent. Water has a chemical formula of H2O.
I think in that box, the one I didn't know what went in there, I think it's H2O. I'm not quite sure why I put a box there because I think you all know that, but oh well.
And here's some 3D models of water molecules. Now, we want to look at dissolving. So let's zoom in on our sugar cube in the water. We're going to look at this edge right here. So here's the edge, zoomed in millions and millions of times. The sugar molecules are all lumped together. This looks pretty confusing, so we're going to clean it up a little. We'll reduce the number of sugar molecules and we'll arrange them in neat little columns. See, this is easier to look at. But just remember, things are more messy in real life. Also, remember that this sugar cube is sitting in water. So, now let's add the water molecules that are on the edge of the cube over here. There we go. We've got the water and the edge of the sugar cube. Now, for the water to dissolve the sugar, water molecules have to bump into the sugar molecules. They got to bang into them, sort of like this. And they can only do this at the surface of the sugar, so it takes some time. Then, after bumping into the sugar, the water molecules kind of work their way in between the sugar molecules and surround them. You can see that happening here. Once a sugar molecule is surrounded by water molecules, they carry it into solution. Here, you can see that one of the molecules of sugar is surrounded by water molecules and it's carried away. Now, keep your eye on this one here at the top, and there we go. It got surrounded and carried away.
Is this similar to the process of dissolving ionic compounds? Yeah. And what happens is that, do you remember what kind of a molecule is water? It has a slightly positive end and a slightly negative end. What do we call that? It is a polar molecule, okay? Sugar also has little polar bits on it. Anytime you see, say, for example, an oxygen, remember oxygen really likes pulling electrons towards itself. And so you can see that the slightly positive hydrogens are pointing towards that slightly negative oxygen. You don't need to know the details of this. It's way too complicated to be trying to analyze this structure for where it's positive and negative, but that's the general idea. Okay, so we have, you know, the negative pointing at the positives pointing at the negative. It works in a very similar fashion.
As the water molecules carry the sugar molecules into solution, new water molecules can reach the undissolved sugar over here, and the process continues. I think this one's next, and there we go. Another one gets surrounded and starts to float.
So if you want to fill in on page 125, if you have not done also already, what do the water molecules do? They collide with the solute. They bump into it. This is on page 125. The water molecules collide with the solute. Then what do? Then they surround the solute. And finally, we've bumped into them, we've surrounded the solute, and what does the water do now? It carries that solute off into the solution.
And this is what's happening at the atomic level as
sugar dissolves. All of these sugar molecules are coming apart from each other, and they're getting surrounded by water molecules, and they're floating off into the solution. Now notice one thing about how the sugar molecules float away. This is super important. The sugar molecules separate from each other, okay? But the whole molecule stays together. The molecules don't break apart into their atoms.
Okay, so the molecules separate from each other. The whole molecules do what? Stay together. Why? Because the covalent bonds, they keep it together. And remember, covalent bonds are very strong, so they hold that molecule together. So it does not break apart into atoms. What are we breaking when that sugar is dissolving? Intermolecular forces. Yay.
In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule.
The atoms in the molecule stay together as the sugar dissolves. So, as you can see, we have 3 molecules that have come off the surface so far, and this process will keep happening, pulling more and more sugar molecules into the solution.
So this is on page 126 now. We'll come back to that little thing on 125. It's just sort of for your interest. Have we lost something? Oh no. Do you want the lights on? Oh, we got them? Okay. Good stuff.
Let's zoom back out and look at our glass. And here we are.
We were just looking at one side of the cube. But this dissolving process is happening all over, on all the different sides, anywhere that's touching water. Now, after the dissolving is complete, all the sugar molecules will have been pulled away from the cube, and the cube is gone. And if we could zoom in and look at the liquid here, we'd see that the sugar molecules are mixed in with the water molecules, spread all throughout. So this is what a solution of sugar dissolved in water would look like at the atomic level. Now, as we've seen, a big part of dissolving is the molecules of solute get surrounded by molecules of solvent. There's a special name for this process. We call it solvation. And we use the term solvated to refer to solute that is surrounded by solvent molecules.
Okay, so what is solvation? Very good. It's when the solid particle gets surrounded by the molecules of the solvent. And when that happens, we say that the solute is solvated. I always like this one. I feel like I should be in some like Baptist church down in the south. Solvation. We're here today to learn all the chemistry, and we will have our solute solvated. Anyway, I'm sorry. I don't know why I feel the need to do that, but I do. And if the solvent is water, we can go one step more than saying the solute is solvated. We can say it is hydrated. Hydro refers to water, okay? So it is hydrated.
Now, if the solvent is water, like it is here, you can be extra precise, and you can say these molecules are hydrated. When we say a solute particle is hydrated, it means the same thing as solvated, but we know the solvent is water.
These little clusters of water molecules surrounding a solute particle are called hydration shells. You might also hear them referred to as solvent cages.
Okay, so they're called hydration shells or solvent cages. I am not going to test you on those words. Okay? Hydration shell, solvent cage. Yeah. But if you're taking things like biology or you're carrying on in chemistry, these will be important concepts. The concept that, you have this surrounding solvent around the solute.
They make this little cage or shell around the solute.
Just keep in mind that they surround the entire solvated particle. So they're actually in 3D, right? Even though we're just drawing them in 2D. So that's hydration shells, solvent cages. Now, let's switch gears here and see.
Shall we do the ionic solutes another time? Just so that we don't get too much all at once, or do you want to carry on? What? My choice. I think we're going to leave this for today, okay? And then we'll have some of those, we'll maybe do a little review for that next time. That'll be good. Yes. How are you guys doing on completing your work in here? Really bad? Could you use some time to work on it today? Because what I'm thinking is your test is coming up next week, so you want to make sure that you've gone through enough of this. I don't want you to do the work for the sake of doing the work. I want you to do the work so that you understand, okay? If you totally understand it and you're doing the problems and you're like, oh my God, why am I doing this? I already know this, then you don't need to do it. Does that make sense? But yeah, I would like to give you guys some time today just to work on stuff, okay? Whatever it is in that book, we've essentially covered everything. So if there's anything in there that you haven't done or that it's been a while since you've done and you've forgotten it, yes, yeah, for sure. I thought today might be a good opportunity to let you get caught up, let you figure out what you do know and what you don't know before we have our test next week. Because tomorrow we're going to be doing a lab. Okay? Borrow a calculator. And did you want to go over that stuff with the calculator?
Yeah.
Yeah.
Is that the one with the scientific notation?
Yeah. Here, I don't think we need to record the rest of this.